Question 17 asks us to find the rate constant and then to propose a mechanism for this reaction using these data. It doesn't tell you that you have to find the rate equation, but you obviously had to realise that that was the first step. You can't find a rate constant without finding the rate equation first. So let's look at how you do that. This is actually quite a straightforward example of this kind of question. If you compare the first two experiments, these two concentrations are the same, and therefore the difference in rate must be down to this, and you can see that the concentration of Fe3 plus has doubled and the rate has also doubled, and so you need to write the explanation of that. You can't just say that shows its first order, you need to spell it out. So you say that when the Fe3 plus concentration doubles, the rate also doubles, and that means that it's first order for Fe3 plus. And then similarly, if you compare 1 and 3, so the first and the last one, this time the Fe3 plus concentration is the same for both, but this one has doubled, and this rate has actually gone up times 4, not just doubled. And so you say that when I minus doubles, the rate increases times 4, which means that it's second order, because it's changing with the square of the concentration. You could actually spell that out if you really wanted to. In other words, i.e. times 2 squared. So therefore it's second order for I minus. And that means that the rate equation is that the rate is equal to K times Fe3 plus times I minus squared. So now we have the rate equation, we can plug the numbers in to figure out the value of K. So the first job is to rearrange that to get K equals, and obviously that just means that we slide these concentration terms diagonally over to that side and get that rate divided by Fe3 plus and I minus squared is equal to K. And we can plug those numbers in. So when you get a question like this, you can choose any one of the 3 rows and use the numbers from that. So we may as well just use the top one. So we get 8.10 times 10 to the minus 4 divided by Fe3 plus is 4.00 times 10 to the minus 2 times I minus squared, which is 3.00 times 10 to the minus 2 squared. And if you crunch all of those numbers, you get 22.5 is the number. And now we have to figure out the unit. By far the best way to get the units of the rate constant is to learn the little formula. You can work it out algebraically just by taking the units of the rate, which are moles per dm cubed per second, and dividing it by the concentration units. But to be honest, that's a little bit error prone unless your algebra is very reliable. So the best thing is to learn the recipe, which is that the units of K are moles to the 1 minus x, dm to the 3x minus 3, and then per second usually. It could be per minute, you have to be careful with that, but in this case, and most commonly it's per second, where x is the overall order, which is the sum of the individual orders. If you haven't yet learnt that recipe for finding the units of the rate constant, I would definitely do that. It's going to save you a lot of struggle when it comes to these kind of questions. So in our example, we've got first order for Fe3 plus, second order for I minus, so the overall order is 1 plus 2 is 3. So we've just got to set x equals 3 there. So 1 minus 3 is minus 2, so it's moles to the power minus 2. 3 threes are 9 times, 3 threes are 9 minus 3 is 6. So moles to the minus 2, dm to the power 6, and then seconds to the minus 1. And that gives us our units of the rate constant. Okay, so the point about the mechanism is that it has to be consistent with the reaction equation, so it's got to have overall 2 Fe3 pluses and 2I minus reacting, but it's also got to be consistent with the rate equation. And the golden rule there is that the order of reaction for each substance must equal the number of particles of that substance reacting in the rate determining step. So in other words, we have to have a rate determining step that has 1 Fe3 plus only, but 2I minus. So when you're asked to propose a two-step mechanism, the simplest way to do that is to make step 1 the slow step. And if it's the slow step, it's the one that determines the rate. So make that explicit like this. Okay, you must write down which step is slow and which is fast, but always explain that the slow step then is the rate determining step. So that's going to be step 1, and then we'll follow that up with a fast step, which therefore doesn't control the rate. So we know from the orders of reaction that that slow step has to have 1 Fe3 plus only, because it's first order, but it must have 2 I minuses reacting to make something. And then in the second step, we've already used both of our I minuses, but we've only used one of the Fe3 pluses. So we need another Fe3 plus coming in here, so that when we add the two steps together, we'll get the 2 Fe3 plus. Now what is formed in this first step is essentially up to you. They're not interested in what the sort of chemical feasibility of your proposed mechanism is. They just want to check that it fits the two equations. So what I would tend to do is to look to see if you can make any of the correct products straight away, because then that means they're accounted for and it just simplifies the whole thing. And you can see that you can make the I2. You can't yet make the 2 Fe2 pluses because you've only got 1 Fe3 plus, but you can make the I2. So let's, as an example, and this is not the only possible answer, but let's do that and then think, right, if we form I2, what would the other product have to be? So of course it's got to balance, and that means that there's only going to be 1 Fe, but we've got to think about the charges. So at the moment the total charge on the left is 3 plus and 2 minus is 1 plus. So if that's just neutral I2, this has to be Fe1 plus. Now it doesn't matter that Fe1 plus looks a little weird and you think I haven't met that before, because it's not meant to be a stable state, it's a reactive intermediate. So although it's formed here, it's then immediately destroyed again because we feed it back in the fast step. So anything that's formed in the first step that doesn't appear in the final equation, you just get rid of it by feeding it back into here. And you can see that that then works out very nicely, because if we add Fe3 plus and Fe plus together, we can get the 2 Fe2 pluses, which is what we needed. So we can just put 2 Fe2 plus there, and that's it, job done. You don't actually need to write any more than that, but I think it's a good idea just as a check, and also to show that you understand how this works, that if you add these two equations together, you get the reaction equation. And you can see that's right, because we get 2 Fe3 pluses plus 2I minus plus Fe plus. Okay, when we add the two left-hand sides together, it goes to I2 plus 2 Fe2 plus Fe plus. And you can see that the Fe plus just cancels out, and that gives you the same equation as that. In other words, it's the correct reaction equation. So that will do. As I say, it's not the only possible answer. You can come up with other slow and fast steps which, when added together, give you the correct equation, but they will only be allowable if the slow step involves 1 Fe3 plus and 2I minus only. Okay, so part B is the Arrhenius question, and it wants us first of all to draw a line of best fit through the data. So you just have to get your ruler up there and do your best. Try to get a line that's as close to all the points as you can, and try and make it so that if there are some below the line, there are some above the line to compensate in a randomish sort of way. So if we draw something that looks like it's going to be reasonable. Okay, so that's a reasonable sort of line. And the point about that is that we can then fit that line to the Arrhenius equation. So on your data sheet, you have the Arrhenius equation written in this form, that the natural log of k is equal to minus EA over RT plus the natural log of A. Now if you just rewrite that ever so slightly like this, natural log of k is equal to minus EA over R times 1 over t plus the natural log of A. So that's basically just opening out that term a little bit. You can see that that's the equation of a straight line. Y equals mx plus c, which remember is the general form of a straight line, because y is the natural log of k, which is our y function. X is 1 over t, which is there. And what that means is that m, remember, is the gradient of a straight line, and that's equal to minus EA over R. So if we measure the gradient of this line, that will give us minus EA over R, and since R is on your data sheet, we can find the activation energy. Also, C is equal to the natural log of A, and that, remember, is the value of log k when 1 over t is 0. In other words, it's that value there. So by using this form of the equation, it's actually very easy to use this straight line to get the values that we need. So first off, we've got to get the value for the gradient. So what that means is that we need a triangle where we can measure then the vertical change divided by the horizontal change, and the thing to do is to make the triangle as big as you possibly can, because that way you minimize the errors in your calculation. So if we look at this, it's about sort of 31.3 minus 27.2, something like that, on our vertical axis, and it's about 0 to 5 across there. So we can write that our gradient is equal to, now it's going to be a negative gradient because the line's going downhill. Okay, so the vertical change is minus 4.2 or thereabouts, so minus 4.2 divided by the horizontal change. Now here you've got to be careful, because if you're rushing you might just think, oh, it's 5, but you've got to check every time you have a graph or a table of data. You've always got to check to see whether numbers have been divided by some power of 10. And here you can see these numbers have been divided by 10 to the minus 3. So we've got to multiply by 10 to the minus 3 to get the original numbers back again. And that means the change along the bottom is not just 5, but 5 times 10 to the minus 3. Okay, and if we work that out, that works out to be minus 840. And as we said, that's equal to minus EA over R. So if we rearrange that, if minus 840 is equal to minus EA over R, then minus 840 times minus R will be equal to the activation energy. And R is on your data sheet, so that's easily done. So it's minus 840 times minus 8.314, which we can just do on the calculator. So we've got 840 times 8.314 equals 6,980. Now the units of that, because R is in joules per Kelvin per mole, this is going to be in joules per mole. And it should have a sign. Remember, energies should always have a positive or negative sign, and obviously the activation energy is a positive number, so it's plus 6,980 joules per mole is your answer for the activation energy. So then we can think about the pre-exponential factor, and as we said, that's the value of the natural log of k when 1 over t equals 0, because then this whole term vanishes if 1 over t equals 0, so natural log of k is equal to natural log of a. So we can therefore write down that natural log of a is equal to this value here, which is about 31.3. And therefore a is the inverse log, which is e to the power 31.3. But on your calculator you can just do inverse of the natural log function. So let's just do that. So we get shift natural log of 31.3 is equal to 3.9 times 10 to the power 13. The units of A are the same as the units of the rate constant, but they generally don't worry about that at A level, and since we weren't told what the order of reaction was, we can't know what the units of K would be, so you just ignore that. They just want the number. Now there's going to be a bit of leeway because obviously everyone will have got a slightly different line of best fit, so you're going to get some variation in your value for the activation energy and also for your value of A. So long as your line is reasonable, you can be confident you would still have got the marks.